All right, how did the first weld homework go? I'm hoping it was, like, really easy, really straightforward. This one will, I would say, be as straightforward also, although there are maybe a couple tricks to it, but those tricks will make sense after lecture today. So let's see. I don't know. I checked yesterday. I think homework 3.4 was still being graded. So obviously 4.1 hasn't been graded yet because that was due today. 4.2 is going to be assigned today. It's due Friday. There's no late submissions on homework 4.2 because I'm turning the solution on right as it goes, right as it's due. Okay. So make sure and get that done on time. All right. And on Friday, we review for our exam because we celebrate on Monday, okay? So, any questions? Okay. All right. Okay. So, we're still utilizing our welded connection limit states, and I finally remembered, by the way, to bring some weld electrodes. So these are some weld electrodes. They come in like this box, okay, and I got one out. I'm going to pass it around so y'all can take a look at it. These are somewhat small ones, I would say, for structural applications. But if you notice here on the box, these are from Lincoln Electric. These are E60 electrodes. So the electrode strength, tensile strength would be 60 KSI, and so we would multiply this times 0.6 to get a shear capacity and whatnot. So I'm going to go ahead and pass these around. I know you've seen these, so, but now we are still utilizing our same limit states that whenever we're looking at a welded connection, we either have the weld metal capacity or the base metal capacity. I'm not going to spend too much time on that because I think we're familiar with that. This is what we added last time, the idea of minimum and maximum weld sizes. Remember, minimum weld sizes arise from the heat sink phenomenon, and then maximum weld sizes arise from the idea that we want to maintain the geometry of the corner of that plate, so we back the weld off a little bit so that we can actually get a defined corner there when we place our bead of weld. Okay, so far so good? All right. So designing a welded connection is pretty straightforward. What we would do is determine the factored load, which again with this, the load could be a dead load, live load, or it could be a gross and net section capacity. We could do that too, the design to develop full capacity. Okay? Now we choose a weld size based on weld limitations first. So we choose our A value. What I'm going to say for the connections that we deal with, at least here in CE 414, is that we're going to choose the largest weld size that we can up to 5/16, and I'll talk more about that a little bit later. We then determine the capacity of a single inch of weld. So the idea is, we determine the capacity of an inch and then we divide to get the total number of inches, okay? And then from there we lay out the connection, okay? Now a couple notes on this. I say that we lay it out usually in a symmetric fashion. I'll explain what I mean by that here in a bit. We typically limit weld lengths to the nearest inch, maybe the nearest half inch, but I would honestly say to the nearest inch is probably fine for most fabrication purposes. And then remember, we use either longitudinal welds or longitudinal and transverse welds. In other words, don't use only transverse welds. Okay, so the procedure I think is pretty straightforward. Let's talk about some background and some things that you need to be aware of when you're designing. Okay, so one of the things that I talked about this a little bit last time, but one of the things that might seem counterintuitive is the idea that we're choosing the largest weld size, which you would think that in design land, typically what we're trying to do is choose the minimum sizes necessary. Like, we do the math, we pick the member, or we figure out how much area we need, and we choose the smallest member that we can that meets that requirement. Well, we're doing kind of the same thing with welds, but what you've got to think about is what we're really interested in when we design a weld is that we provide enough weld area, okay? So the idea, like think about a rectangle, right? Let's say you need a rectangle that's 16 square inches. You could do 1 by 16 or you could do 8 by 2, right? Okay? Both of those have the same area. So I propose that from an economy standpoint, what we want to choose is the largest A value. The largest A value means that we need the shortest weld length, which means it's quicker to deposit. And so it's more economical from a fabrication standpoint. Okay? So typically we'll go with the largest weld size possible. Okay. Now one of the things I said in the last slide is that we're going to choose the largest weld size possible up to 5/16. Okay, let me sort of explain why. Let's say I have a weld that I'm placing. Okay, so I place a bead of weld. So there's a bead of weld. Okay, so again in 3D, so it's going in and out. Okay, I propose that the largest weld size that you can deposit feasibly with a single pass of the electrode is like 5/16. Okay, so let's say for the sake of discussion that I need to deposit a really, really big weld, a weld that's like 3/4 of an inch, like a really big weld. Well, the only way to do that is to take the electrode, place a bead, and then place another bead, place another bead, place another bead. And so what you're doing is you're building that weld up until you get the size that's needed. Okay? So typically what we want to try and do is place welds with a single pass of the electrode, which is faster, faster, more economical. So the largest weld that we can deposit is about a 5/16. Oh wow, I drew that and then it was right over the box. Man, that's crazy. Knowing my luck, I'd draw it right over the box. Okay, now that doesn't mean that you don't need to ever have welds larger than 5/16. I mean, that's entirely possible that you're designing a connection and the weld needs to be larger than that, but it's typically only needed if the loads are really, really big. Okay, so if most routine connections in building systems like beam to column, things like that, you can probably get by with a single pass. Never lay out a connection that has only transverse welds. Again, poor performance and ductility, we talked about that last time. Never do that, okay? So I'm not going to harp on that too much because we talked about it last time. Just don't do that. Okay, everybody with me so far? Okay, now let's talk about arranging welded connections. And so up until now, what we've been dealing with are symmetric arrangements. Okay, so what I mean by that is, let's say that we're designing a welded connection for just a plate. So we have a plate lapped on top of another plate. And we do the math, and we find we need 20 inches of weld. Well, how are we going to lay that out? Well, we'll probably put something like, I don't know, 10 here and 10 here, right? Move on, right? Symmetric. There really wouldn't be a reason to place all the weld on one side or 15 inches up here, 5 up here, okay? First off, I think that in your gut that probably doesn't make sense to do that, to have a connection laid out in a fashion where there's more weld on one side than there is on the other. But that's especially true for connections like this, where the centroid of the member falls right through the middle, right? So the analogy that I would give you in this case is we're sort of talking about like imagine that the supports are the welds, right? Okay? And the load is, I don't know, point load right here in the middle, right? So if you have a point load, that's P over 2. That's P over 2. With me so far? Right? So I need to generate enough weld to resist those reactions, right? Okay. This is a symmetric arrangement. What about a balanced arrangement? Okay. Now with a balanced arrangement, I said something in the prior slide. I said sometimes I guess on a connection like this, it wouldn't make sense to use a longer weld here than it does here. But I argue that it does make sense here. Okay. So what I have here is I have an angle, okay? So I have an angle welded to a plate. So what we're kind of looking at is, you know, like an angle, and I've got a weld here and a weld here, okay? And I propose that this weld here on the back should be a little bit longer if you're trying to generate a balanced arrangement. And what do I mean by a balanced arrangement, or why would it need to be longer? Let me give you the analogy here over here. So what we're talking about here is, you know, here's your beam. Bless you. Again, the supports are the loads, or sorry, the supports are the welds, but instead of the load being in the middle, notice where the centroid of an angle is. It's up here, right? It's not halfway. It's going to be hugged closer to that back leg. So this would be like if we had the load over here. So if the load is, you know, like all the way over here, maybe we have, I don't know, a reaction that's like this. Like 0.8p and 0.2p. So we need a longer weld on this side in order to be able to resist that. Does that make sense? So in a balanced arrangement, we're trying to provide the welds such that they are proportional to where the centroid is. And the reason for doing that is we would try and arrange the welding to where there's no bending in the member, okay? Which is usually advantageous in fatigue-prone scenarios, earthquake-prone scenarios, things like that. So that's why you would do a balanced arrangement. And so to explain how a balanced arrangement works, but also just how to design a welded connection, we're going to do this problem, okay? So I'll tell you this problem is harder than the homework, so if you can do this problem, you can definitely do the homework. So we're going to design balanced welds to resist a design load of 150 kips. I've already factored the load for you. Let me pull up the notebook here. Sorry. All right. So we're going to design for a load of 150 kips. We have an angle that's 6 by 4 by 3/8. Okay. And I guess I should clarify right here, but maybe I'll go ahead and do this here, that this dimension is the 6 inches. In other words, if you had an angle that had a longer leg on one side, that longer leg would probably be the one that you would connect to the adjacent member. We really wouldn't connect the short leg to the adjacent member. Okay. Okay. Everybody with me so far? All right. Okay. So step one is to choose or to factor the load, but we were given the factored load, so we don't need to worry about that. We know our load is 150 kips. So what about step two? Step two is to choose our weld size. Okay. Now in this problem, we're going to assume the gusset plate is adequate, so we're not really going to worry about that. All we're going to worry about is the angle in this case. So for the angle, in order to choose a weld size, we're going to need to account for its thickness. And in this case, the thickness is 3/8. Okay. So what I need to do is I need to figure out A min and A max. How do I determine A min, by the way? You look it up. So what is A min going to be if the thickness is 3/8? What is it? A min? Somebody didn't bring their AISC 16th edition steel construction manual.
I got it.
Oh.
Trying to remember.
You need an 8-minute cycle truck to get that book out of the man. 3/16. Okay. Now how about A max? So that one we calculate, right? So that one, we say it's either the thickness or the thickness minus the 16th. Am I going too fast on this? I'm hoping by now you all just did a homework on it, so this should be pretty familiar. Okay? Okay. So that's going to be 3/8 minus the 16th, so 6/16 minus 1/16, that's 5/16, right? Why do I have a tendency to put that little inch sign on the bottom? It's on the top. Okay. So, given this range between 3/16 and 5/16, what do we choose? The 5/16. So we choose the biggest that we can up to 5/16, okay? And by the way, all right, just to make sure we're on the same page, what if that was the case? What would we choose? A 1/4 inch, right? What do we choose here? 5/16. Okay, we're all on the same page. Or let's make sure. Is everybody on the same page? Okay, good. All right. Does anybody have any questions on this? Okay. So we know our weld is going to be 5/16. Okay. So now what we need to know is we need to know what we're working with. Okay. So okay. So now what we're going to do is we're going to determine the capacity of a single inch of weld. Because what we want to know is how many kips can each inch resist. Okay? And so the way that we're going to do this is we're going to look at all 3 limit states. Okay? But let's make this a little easier. Okay. Okay. What was FY and FU? I don't think we ever looked that up. This was A572 grade 50, right? So that's going to be 50 and 65, I think it is. What about my electrode strength? 70. Okay. All right, so we've got 3 different limit states that we need to assess. So what are those? Those are weld metal capacity. We have base metal shear yielding, base metal shear fracture. And so what we're going to do is we're just going to compute the capacity of all of those using these terms. So let's see what we get. So this is the part that just has a lot of writing. Okay, and if you want, I'm lazy, so I'm just going to leave the 1 inch off because it's just, just multiplying by 1. And I'm going to get a value. It's going to be kips per inch. I'm hoping that's, am I going too fast on this? I'm hoping this is easy. Tell me if I am. So what do we get for this? 6.96. 6.96. Okay. So now what we're going to do is base metal yielding. What was the phi value for this?
1.
There we go. Now, by the way, what is AGV in this case? What is it? What is the gross area of the base metal under shear?
1 times the thickness of the weld.
1 times is it the thickness of the weld? Thickness of the plate, right? In this case, the thickness of the angle leg. So what I'm going to do, just 3/8, right? 3/8 times 1, okay? Because again, the weld length is 1 inch, right? Because that's basically what we're doing, right? AGV and A and V equals LWT. So, all right. So, what do we get for this? Second? You ought to not do the next one.
Yeah.
Make everybody else put in some work. So. Okay, so one more. So really, the only thing that changes is our phi value changes, and we go from FY to FU. So. Okay.
10.97.
10.97. Do I have a second? All right. All right. So we have three values. Which one are we going to use for laying out the connection? The smallest, right? So therefore, we're going to take okay. Okay. Now the problem gets fun. Okay. So I would argue that everything up until now was admittedly a little boring. Now it gets fun. But before we get to the fun stuff, let's make sure the boring stuff made sense. Everybody good? Okay. Okay. Now, if we were doing a plate, how would we do, okay, let's take a step back. Let's say this wasn't an angle. How would we do this? I mean, I'm asking. What would we do from here? What do we know? We know the capacity per inch, 6.96 kips per inch, and we know the load. So tell me what we would do.
Take the load divided by the kips per inch, and then find the inches of weld needed.
And if we were welding a plate as opposed to an angle, then what we would do?
Divide by 2 to apply to both sides.
Half and half, right?
Yeah.
Maybe what we'll do is put a transverse weld, take the difference, and then half and half of that, right? But that's basically it, right? Everybody with me so far? Okay. Because we're dealing with an angle, this part gets a little bit more intricate. Okay. So a couple things. So we are applying longitudinal and transverse welds. Okay? Now, what was the angle again?
6 by 4 by 3/8.
I'm going to need something from you on this. What's X bar and Y bar?
Y bar is 1.93.
Okay. Y bar is 1.93. And this is
0.933.
okay. And by the way, let's just have that there. Okay. You go away. Okay. So let's see, how do we want to do this? All right, so first thing I'm going to do is I'm going to draw a front view and a side view of the angle, okay? So what does that look like? Okay, so I've got here's the angle. And then that's the leg of the angle, right? So what am I drawing? Just this, right? Okay. And then over here, go away. Is that? Is everybody with me on that? Okay. Now, this dimension right here is 6 inches. Okay. Now, the centroid of this angle, let's do this in blue. Centroid of this angle is going to be something about like that. Let me scroll this up a little bit. That's going to be the centroid, right? Through both the front view and the side view. Okay? And it is through the centroid that PU equals 150 kips. Okay. Now, here's what I'm asking you. Okay, so would you agree that dimension is 6 inches, right? This dimension is what? Okay? So then the question is, what is that?
1.93 inches.
It's Y bar. It's not X bar, it's Y bar. Okay? Does everybody see that? Y bar goes from the short leg to the centroid. X bar goes from the long leg to the centroid. Okay? So this dimension is Y bar. Okay. Everybody with me so far? Okay. Now, on my front view, I have the PU of 150 kips going to the right, okay? So statics tells me I need to have 150 kips going to the left. So where do I get that? Okay, I propose that I get that from a weld here, a weld here, and a weld here. Okay? So what we'll do is we'll call this F1, F2, F3. Okay? Now, I drew the arrows for F1 and F3 like, I drew this arrow a little bit down, but really F1 is going right through here. So really, if we wanted to accurately draw F1, it really sort of, you know, like be like that. Same thing with that. Now, F2 is a weld. How long is the weld?
6 inches.
So where is the middle of that weld? Okay, so would you agree with that? How much force, now let's talk about F2. How much force can that weld supply or generate?
6 inches times
Okay, 6 inches times 6.96. Okay, and where do you get the 6.96 from the capacity? So, okay, and if we chug that out, we get this. Is everybody okay with this? Okay. So do you remember I told you that there was a beam analogy with this? Like I drew a beam? So how many unknowns do I have now? 2. This and this. Let's go back to statics and structural analysis. I have 2 unknowns. Well, actually, I had 3 unknowns, but I was able to figure this one out just by the length. Do I have any forces going up and down? All I have is forces going to the right and left, and I have sum of forces in the x direction equals 0, and I have sum of moments equals 0. Is that right? So maybe what I'll do is sum moments. So we'll sum moments about the back of the angle. Okay. Do I need to consider F1 if I'm summing moments about the bottom? Okay, what about F2?
Yes.
Okay, so F2 about the back is going like this. So that's F2 times what moment arm? What about F3? What's its moment arm? What about PU? Does it generate moment? The other way, right? Times the moment arm of Y bar, right? Y bar of 1.93. What do I not know in this expression? What's the unknown? F3. Because I know that and that, and I know that. So, all right, so how does my algebra work this morning? PU. Did I do that right? Subtract that over, divide by 6. How did I do? So, actually, let's do this lower. So is everybody following through what I'm doing here? Okay. So what is F3? And we'll say like 2 decimal places because that's enough. Say it again. 27.37. I got something a little different. 2587. That's what I got. Something like that. That's 41.76, and that's 1.93. 150. Might be a typo. But did everybody else get 2587 or something? 25.9, 25.8?
I I got 2737.
You got 2737? Okay, I believe you. I did something wrong then. 0.2 on the mistake counter. I get partial credit too, thank you. If you want to start doing full mistakes, we can do that. We'll start talking about partial credit. That was wrong. That was mean. That was really mean. Okay, so, oh, that's not inches. That's kips. Okay, so now what do I do? Tell me what to do. Oh, okay, yes. So we would divide to get the inches as well. I'm going to do that part last. Okay, what do we get? What force am I missing?
F1.
How do I get F1?
Set moment on top of.
Well, we've already done moments. Let's sum forces, right? Because we know that F1 plus F2 plus F3 equals the load. So, could we just say just subtract, right? What do we get?
80.87.
Say it again.
80.87.
Second? Okay. I like it. Okay, so now, as Mr. Foster said, now what we can do is determine the lengths of the welds. And how do we determine the lengths of the welds? We do that. Okay. So what do we get for these?
11.62.
And this one.
3.93.
Okay. So I'm not going to tell a fabricator to place a 3.93 inch weld. So I'm going to say 4 inches, 12 inches. Okay. So I guess my question is, what's the answer? Here's what the answer is. Okay. Here's our angle. Actually, let's make that a little higher. And how long is this weld going to be? That's going to be the answer. And I'm trying to utilize like welding terminology, welding symbols and whatnot to indicate what we've got going on. All the welds are 5/16 in size. They're all fillet welds. 4, 6, and 12 are going to be our lengths. And that's the answer in terms of laying out the connection, okay? We take a step back. How are we doing? Not bad, right? You got the weld lecture or you had? So don't forget. Okay. Sound good? All right, so I've given you a homework assignment. The two things that are different on that assignment are as follows. Number one, it's an equal leg angle, which should make your life a little easier on determining centroid distances. But what is clear, that is the big difference, is that there is no transverse weld, okay? The homework assignment is only longitudinal welds, okay? So let me make sure I'm right on that. I'm fairly certain I did that one on this one. I made the homework last week, so. Yes, longitudinal welds only, okay? So in the case of longitudinal welds only, could you utilize the calculations we did so far, we did in this example? Well, you could, as long as you set a certain value equal to 0. Maybe F2? Because there is no F2, right? There is no F2 because there is no transverse weld. So again, what I'm getting at, that's sort of what I meant when I said this problem's harder, you know. If you can do this, you can do that, so. Sound good? Due Friday, no late submissions. That's all I got, everybody. I'm going to pull the code up one more time. Exam review on Friday.